Welcome to this lecture. So far we had looked at some basic concepts in real time operating systems, and then we had said that the scheduler, task scheduler is actually the most important part of any real time operating system, because it is the one which takes the primary responsibility in meeting a task's deadline. We had also looked at resource sharing problem in real time operating systems, and we had looked at protocols to help solve the problems that arise during resource sharing. This lecture we will continue with some basic issues that arise in real time operating systems, and after that we will look at whether Unix can be used as a real time operating system, what problems may arise if we use Unix as it is, and how it can be extended. So, let us get started with the basic issues in real time operating systems. One of the most crucial requirement is of course support for real time priority levels. What we mean by real time priority levels is that once the programmer assigns priority to the tasks, the operating system does not change it. So, these are static priority levels, but as we will see that the traditional operating systems change the priority of tasks dynamically. Real time task scheduling policy, this is one of the central requirements of any real time operating systems. Support for resource sharing protocols, because without use of proper resource sharing protocols there can be priority inversions and tasks may miss their deadline. Low task preemption times, the order of milli or microseconds. When a high priority task becomes ready, the low priority task that is executing must be preempted, and this preemption time is of the order of milli microseconds. The interrupt latency requirements. Once the interrupt occurs, it must be recognized and the interrupt servicing must occur within some bounded small time. Additional requirements on real time operating systems are memory locking support, because in a virtual memory system the page is replaced if it is not used, and therefore, when a page fault occurs it can take a long time and introduce jitters. We will just look at this issue, and that is the reason why one of the basic requirement for an operating system to serve as a real time operating system is the support to lock memory, and these locked pages will not be subject to page swapping. Support for timers, both periodic timers and one shot timers, high precision timers. These are frequently required in writing real time applications and need to be supported by the operating system. Real time file system support. The traditional file system, the blocks are written based on where space is available on the disk, but then the access time of the blocks varies depending on where it is located on the disk. In a real time file system, the blocks are written consecutively, so that the access time to the blocks becomes predictable. And finally, the real time operating systems should facilitate device interfacing, because many of the real time systems, they incorporate many sensors, actuators and so on. Using a new type of sensor or actuator should not require to rewrite part of the operating system. The device drivers for these devices should be able to be incorporated on the fly. Do not have to really shut down the system, recompile the operating system and so on should not take place. First, let us look at the real time priority levels. The real time priority level implies static priority level. That is, once a priority is assigned to a task by the programmer, should not change. The operating system should not change a programmer assigned priority. On the other hand, in a dynamic priority, the operating system keeps on changing the priority level of tasks. You might wonder that why does the operating system needs to do this? We will see this in some detail in this lecture or possibly in the next lecture, that all traditional operating system, they change the task priority after every time slice. The main reason is to enhance the throughput of the operating system. The task scheduling support, it is seen that task scheduler is a central aspect of any real time operating system, and therefore, the real time operating system should support task schedulers like rate monotonic scheduler, earliest deadline first scheduler and other custom task schedulers. Resource sharing support. So, tasks in a non-trivial application need to share resources. For example, the results of one task needs to be passed on to another task. They may use a shared memory for this. They may use a shared device and so on. And we have seen that the traditional operating system solution to resource sharing, which is the semaphores, leads to priority inversions and unbounded priority inversions. And we had seen protocols like priority ceiling protocol. The real time operating system need to support the priority ceiling protocol, so that the high priority tasks do not miss their deadlines due to the priority inversion problem. The task preemption time need to be low and bounded. When a high priority task becomes ready, the low priority task must be context switched and the high priority task must run, and that should be of the order of few microseconds, because the task deadline is hundreds of microseconds. So, if the task preemption time is hundreds of microseconds or a second or several milliseconds, then it is likely that the hard real time tasks will miss their deadline. In the next lecture, we will look at Unix as a real time operating system, and we will see that one of the major problem is that task preemption time in Unix is of the order of a second, and therefore, if a hard real time task has a deadline of 100 microsecond or something, then the task preemption time itself is going to cause a deadline miss. But then you might be wondering at this point that why is that the traditional operating systems like Unix have such a high task preemption time of a second or something. We will see this issue in slightly more detail, but right now let us just understand that the kernel of a traditional operating system is non-preemptive. What we mean by non-preemptive is that when a interrupt occurs, the kernel does not service it. Actually, the kernel disables when in the kernel mode. Again, that will raise many questions in your mind, that why does the kernel have to do it, that it disables all interrupts when executing kernel routines, and why does it have to be a second, and so on. We will look at this point in more detail, but right now we will just mention that the large preemption time is due to the non-preemptive kernel, and the kernel disables interrupts when executing kernel routines. There are also interrupt latency requirements on a real time operating system. What we mean by the interrupt latency is that when an interrupt occurs, and by the time the interrupt service routine runs for that interrupt, the time must be small and bounded. Let us look at this diagram. At this point an interrupt occurs. The interrupt is recognized by the operating system, and then it does some processing, for example, saving the current set of registers and so on, and then it runs the interrupt service routine. So, the point where the interrupt occurs, the time point at which the interrupt occurs to the time point where the interrupt service routine starts running, we call it as the interrupt latency time. And for traditional operating system, this time is large, of the order of a second, but then for a real time operating system, this time should be of the order of few microseconds. And also the time bound on the interrupt latency must be deterministic. That is, once we say that the bound is, let us say, 10 millisecond, in no case it should exceed 10 millisecond. We should be able to give a deterministic bound on the interrupt latency time. But then you might wonder that how does such low interrupt latency is achieved by a real time operating system. Because when a interrupt service routine is running, it may take several microseconds, and in the meanwhile if another interrupt occurs, then there will be problem. It has to keep on waiting. The way in which many of the real time operating systems achieve low interrupt latency is by performing much of the interrupt service routine as a deferred procedure call, which runs like any other task. These are queued as low priority task called as deferred procedure call. Therefore, as soon as the interrupt occurs, the code that runs is a very small code that creates the deferred procedure call and queues it up. As you will see that this is the main technique that is used to achieve low interrupt latency. For the traditional operating system, not only that the kernel should become preemptive, that is, even if it is running in the kernel mode, the kernel code is executing, still it should be able to preempt the kernel code, and also we should be able to handle nested interrupts. That is, when the interrupt service routine itself is running, further interrupts should be recognized and should be able to process it. There are requirements on memory management. For example, in the virtual memory system and in the memory protection features, we need improvement. Of course, in a very small embedded real time operating systems, where the task size is small, only very few tasks, and the overhead of the operating system needs to be very small, the footprint or the size of the operating system need to be small, then the virtual memory is not supported. And even the memory protection feature, that is whether one task can unintentionally overwrite the results of another task or the code of another task, is not guaranteed by the operating system, because that would require additional overhead, and we need only a very small size operating system, and therefore, many of the embedded real time operating systems do not really support virtual memory and memory protection systems. But unless we do something for, let us say, non embedded applications, or where in embedded applications where you can afford to have large sophisticated operating system, we need to do something so that the worst case memory access time is not increased drastically. We will just look at that issue, because unless we do that, there will be memory access jitter. What we mean by memory access jitter is that if the data is sometimes obtained very fast and sometimes obtained after considerable delay, the variation in access time is called as the jitter. In a virtual memory operating system, if the page is resident in memory or in the cache, then the access time is very fast. Very quickly the data is obtained by the processor, but if the page is not available on the memory and the page fault occurs, then the hard disk needs to be accessed, and the access time becomes hundreds of times larger than when it is available in the main memory. We need to do something to prevent such memory access jitter times, otherwise this will lead to tasks missing the deadline. Virtual memory, which you might have studied in a first level operating system course, it helps to reduce the average memory access time, but then the worst case memory access time degrades, because if the page is not available in memory, a page fault occurs, and then it has to be obtained from the hard disk, and the page faults incur significant latency. But the virtual memory also has memory protection as a offshoot or as a byproduct. All virtual memory systems, they support memory protection feature, that is, each task can access only those part of the memory for which it is entitled. It cannot really access the entire memory space, that is all the data that is resident on the computer. This is called as the memory protection feature, and if for some reason we do not support virtual memory, maybe because the operating system needs to be small embedded system and we cannot really afford to support a virtual memory system, then memory protection becomes a issue, because without memory protection, if there is a error in the operating system code, it becomes very difficult to debug, because the code, the operating system code is overwritten when there is no memory protection, and it just crashes. You cannot find out where exactly it is overwriting and so on. And also, without virtual memory support, memory fragmentation becomes a problem. Naturally, a question arises, which are the types of the real time operating systems which support virtual memory. We need virtual memory when the tasks require large data or the code is significant, that is to meet the memory demands of heavyweight real time tasks which have large code or require large data, we need virtual memory system. And also if we need to support running non real time applications in our system like text editor, email client, web browsers, etc., it becomes necessary to support virtual memory as part of the real time operating system. But let us look at memory protection. We said that each task has its own address space. A task cannot access the address space of another task, and that is ensured by the memory protection mechanism. When we do not have memory protection, all tasks operate on the same address space. The advantage of having a single address space that it is efficient. No checking of protection bits etc., is necessary, and also it saves on the memory bits required to ensure protection. Therefore, the calls become lightweight, that is efficient, and require also less memory. For very small embedded applications which require only one or two small tasks which the programmer can easily manage, then memory protection may be done away with. But for applications having many tasks, it becomes very difficult to work without memory protection. So, for very small embedded applications with just a small memory and a small number of tasks, memory overhead in the form of protection becomes unacceptable, and the programmer can easily manage to program the application even without memory protection. But then for larger application without memory protection, the cost of development of the program increases, because debugging becomes very hard. One task can overwrite the data or the code of another task. And not only that, the maintenance cost increases. Later you want to change something, becomes very difficult to change the application. If virtual memory is supported by a real time operating system, then we need the memory locking feature. In the memory locking feature, the programmer can lock a memory page. It prevents the page from being swapped from the memory to the hard disk, and therefore, the jitter in memory access reduces. In the absence of memory locking support, even the critical tasks can suffer large memory access jitter, and therefore, the task scheduling has to be extremely conservative, and still the tasks may miss their deadline because of this memory access jitter. The real time operating systems also need to support asynchronous I/O. The traditional I/O in a operating system is synchronous, that is, a process blocks when it waits for the result. For example, you are doing a word processing application and you want to save the file. While the file is being saved, you can't do anything because it is a synchronous call. But if you are given a save command and at the same time you are able to also do editing and other operations, then it is a asynchronous I/O, also called as a non-blocking I/O. You can initiate the I/O and then continue operating, and calls such as asynchronous I/O read, asynchronous I/O write, these need to be supported by real time operating system, because I/O is typically slow, and if a task process has to block on account of I/O, then it may miss its deadline. Becomes very difficult to program a real time task without the support of asynchronous I/O. Also, if the real time operating system is to be used for embedded systems, then the size of the operating system, sometimes called as the footprint of the operating system, needs to be very small. The other feature that is desirable for embedded applications is the power saving feature. The operating system should take responsibility to save power, that is run the processor in low frequency mode when the load is not high, switch up the processor part and so on when the load is not high, and that is how conserve the power. So far in this lecture, we looked at what are the features that set apart a real time operating system from a non real time operating system. We identified about a dozen features which an operating system needs to support in order to be called as a real time operating system. To make the issues clear and to get a deeper insight into these aspects, we will consider what problems may occur if the traditional Unix is used as a real time operating system, and what is the origin of these problems, because unless we know these issues well, we cannot be able to really develop a real time operating system. If we want to use Unix as a real time operating system, we will find many problems. Actually, all the problems that all the issues that needs to be supported by real time operating system that we identified in this lecture are not satisfactorily supported by Unix. But then there are two problems which really stand out. One is the non preemptible kernel. When the Unix operating system is running the operating system code, interrupts are disabled. And the second point is dynamic priority levels. Even if the programmer assigns a priority to a task, the operating system keeps on shifting it the end of every time slice. This lecture, we are almost at the end of the time. We will just look at these two issues, because these are crucial issues to understand why a traditional operating system cannot be used as a real time operating system, and also why these problems are there with a traditional operating system in the first place. With this, we will just conclude this lecture, and we will continue from this point in the next lecture.